yeah, you can expand it if you want
If
to.
you click the top and drag it to one of the sides of the.
That's good, that's good. Oh, well, we don't really, you've already got it up here. I'm gonna type this into here, but for you, I could change this to U1 and U2 so that the axes would be appropriate labeled, but I'm not gonna do that. My U1's gonna be the X's, and my U2 is gonna be the Y's, all right? So I need to change, the first thing I need to do is change those equations. So I need minus the quantity 13/8 times X, and then I'm going to have plus the quantity 3/4 times Y plus 14. So that's the first equation. Is just I've just typed this equation, substituting the X for the U1, the Y for the U2. All right? And so then I'm going to get on this one, 1/4. Don't forget the times. I think it gives you a warning if you do forget it. Minus the quantity 1/4 times Y. All right, now, the next most important thing is we need to know where are we going to look. Well, we know we've got an equilibrium at 16, right? Okay, so I guess it doesn't really matter. Let me just say, well, realistically, the minimum value should be zeros, right? Okay, actually, temperature could go below 0. But
Why do you know the equilibrium's at 16? What did you?
We solved this problem last time.
Oh, my bad.
This is not new stuff in the sense that we are doing the greenhouse problem that we've already solved, okay? All right, so the next thing you want to do is you want to tell what's the plot region we want to look in, okay? And I've gone ahead, let me change that, let me just change that to 25. No particular reason. All right, and then I'm just going to tell it, proceed. Okay, I'll make this one a little bit bigger. Okay, and now, that looks like a direction field, doesn't it? Wouldn't that be a lot of fun to calculate by hand, every one of those arrows?
Mm-hmm.
All right, and that's all it did. What did it do? It just gridded this thing up into 20 spaces between 0 and 25 and put 20 arrows in this direction, 20 arrows in this direction, each of them pointing in the direction of the dot, right? This tells how much going in this direction, how much going in this direction. And that creates the little arrows there. And so you can already visualize sort of where it's going. Now, one of the little tricks I talked to you about, I mentioned the idea of null clines, where the U1 dot is equal to 0 and where the U2 dot is equal to 0. There turns out up here under solutions, okay, lots of different options up here. We'll talk about a few of them at different points. But let's just go ahead and start by showing the null clines. Now, the significance of the null clines, all right, didn't I tell you that when U1 dot equals 0, those things have to be crossing vertically? So this purple line, you can see the trajectories are going to be crossing it vertically. Okay? And then obviously on the orange line, it's crossing it with U2 dot equals 0 horizontally. Okay? And then where's the equilibrium going to be? The intersection of the null clines will always, so one of the reasons for the null clines is you need to find the equilibrium, right? And we sort of know it should be 16, 16, doesn't that look like 16, 16? But what's really nice, we come to the solutions, we say find an equilibrium point, put your little arrow somewhere near there, you don't even have to be dead on it, and it finds it. Okay, now did you see anything else happen when I clicked on it? Came up with this window. That that window's really powerful for you. Specifically, this one computes the Jacobian. Now, the Jacobian's not very interesting in this one because we've already know what the Jacobian is. They're there, they're constants. Okay? In the nonlinear case, it's going to be not so easy. Here you can see, aren't those the constants? That's that matrix. What else? Now, this again being MATLAB, what can it easily do with that matrix? It can find eigenvalues and eigenvectors. And so it does that. It finds eigenvalues and eigenvectors, and it tells you at 1616 we have what's called a nodal sink. We're going to usually call it a stable node. Yes?
So to graph the functions on top of the slope field, you just do regular.
So you're ahead of me in this sense. So if you want to see a trajectory, say, okay, I like the trajectory coming from here. Click. Oop, there it is.
Whoa,
Oop, there it is.
that is so cool.
Click. There it is. Oop. It goes backwards and forwards, and by the way, you can adjust it so it only goes forward in time. You can so it only goes backwards in time. This one I'm just letting it go backwards and forwards. Click. Oop.
But that's different with different constants, right?
So this is different initial conditions.
Right.
So starting with different initial conditions, this is one trajectory coming like this. Here's another trajectory going like this. And so we can see how if we vary where we start, what the trajectory looks like. And the nice thing about this is it just does a nice, beautiful solve. And it has ways of modifying those solvers and other stuff. So there, we have a phase portrait. Beautiful, easy phase portrait. Can't get much easier than that, can it?
Can you make the arrows darker?
I don't know how. You're welcome to look it up. But I can tell you this code's about 5,000 lines.
Oh god.
I'm good.
A MATLAB program I'm excited to use.
Wow.
Damn.
Okay. So here's one that's really easy to use, and I hope that helps you see the pictures we were looking at for the behavior of our greenhouse problem, right? Pretty easy to visualize what's going on. And that's what I'm trying to get, is we're going to be able to visualize these different ones. But I do want to emphasize this thing is very powerful. Now notice, one of the things I don't like about MATLAB is, you notice those eigenvectors have got some pretty weird little numbers there. The reason it does those pretty weird little numbers there is it always calculates the norm 2 of the vector equaling 1. Okay. Generally, we like nice integers. Okay. All right. Any questions on this particular one? Yes.
What?
These next questions.
So if we put the eigenvalues and eigenvectors, the eigenvectors that the program gives us into
It'll work.
okay.
Well, yeah, it's got 5 significant figures. It'll work.
Okay.
So it should work with that. It's yeah, because an eigenvector what is any constant multiple of that.
What's wrong with that?
So we can look at, for example, this particular one. What would be a better choice for an eigenvector here than this minus 0.4 or minus 0.8? Anybody see nice integers that would be nice ones that would work here? 1 and 2. Wouldn't 1, 2 be a nice eigenvector there? And that's one we count. Yeah, I think we calculated that last time. All right, so you can do this quite easily. Good enough?
That was it. I was just asking like what vector it gave you, but it's just random, right?
No, it's not random.
The constant. Oh, it's the one that you picked.
No, so that's the thing I'm telling you, that in MATLAB, it always does that the norm of V in the 2 norm must equal 1.
English? I'm confused.
Learn about norms. Didn't you learn in linear algebra that all the norms are equivalent? Yeah. And the common norms you work with are the 1 norm, the 2 norm, and the infinity norm. Right? You did that for vectors and you did it for matrices.
Oh, I get it. Thank you.
Okay?
Got it.
And what MATLAB
That was
does,
confusing.
the point is the 2 norm is the Euclidean norm, it has to do with the distance. So this is looking at vectors that are on the unit circle, is what it's doing. All right, let's go back to where we were.
Okay, I'm gonna stop this now.